Hello everyone, this is our heat transfer, transient heat conduction video discussion for group 9. The group members are me, Harbin Singh, Noor Irina Jiha and Lim Jazem. Okay, for this week we have the question number 9. A thick wall made form of refractory bricks with thermal conductivity K of 1 watt per meter K and thermal diffusivity alpha is equals to 5.08 times 10 to the power 97 meters square per second that has a uniform initial temperature of 15 degrees Celsius. The wall surface is subjected to uniform heat flux of 20 kilowatt per meter cube. Thus, for this question, we must use Excel or other software to investigate the effect of heating time on the temperature at the wall surface at x equals 1, x equals 5 cm from the surface. Okay, let the heating time vary from 10 seconds to 3600 seconds and plot the temperature at x equals 0 at the surface and x equals 1 and 5 cm from the wall surface as a function of heating times. For this question, we use the equation T equals to T initial plus Qs over K, which is the thermal conductivity, and then it's bracket times by 4 thermal diffusivity time over pi, which is the square root, and exponent to the negative of x squared over 4 alpha t. Okay, that's the equation. Okay, next, the assumption that we made is the heat losses from the brick is disregarded, thus the Tmax is obtained from the result. So the T that we calculate temperature is the temperature maximum that we regarded the heat loss. Next, the brick is sufficiently thick to be treated as a semi-infinite solid. The properties of the brick is constant, such as the thermal diffusivity and thermal conductivity. Okay, and the error function in the equation is eliminated as it is very small compared to the temperature that we obtained. Okay, next, the properties are thermal conductivity K is equals to 1 watt per meter Kelvin. Thermal diffusivity alpha is equals to 5.08 times to the 10 power 97 meter squared per second, and the initial temperature at the surface is given at 15 degrees Celsius. Okay, the heat flux is Q equals to 20 kilowatt per meter cube. Okay, the heat flux is given at Q dot. Okay, that's all. Okay, then this is our equation just now.
The data analysis for this question is that we assume it is transient condition problem in a semi-infinite medium subjected to a constant surface heat flux. This is the formula used in this question, which is Ts T surface equal to T initial plus Qs, which is heat flux over K thermal conductivity, multiplied by square root 4 alpha times over pi.
For this question, we used Excel software. As you can see, there are three tables: table 1, table 2, and table 3. As you can see, for the table 1, the x is 0 meter from the wall surface, so this temperature will be the temperature at the wall surface. For the x, for the table 2, the x equals to 0.01, so this temperature will be 0.01 meter from the wall surface. And the third table, the temperature will be 0.05 meter from the wall surface. So as you can see, the thermal diffusivity and the times is here. Okay, thermal diffusivity is 5.08 times 10 to the power 97, and the heating time start from 10 until 3600 for every table. So the value of T obtained for the 0 meter from the wall surface is at 65.86, and it go until 3600 seconds. Wait, so it's at the bottom here. So at the 3600 seconds, the temperature at the wall surface will be at 980 degrees Celsius, and at the x equal to 0.01 meter from the wall surface, it will be at 966, which is a bit lower. Okay, for the x equal to 0.05 meter from the wall surface, which is the most innerst part for this question, so most furthest from the wall, so we are at 700 degrees Celsius. So the most highest temperature is at the wall surface, and it gets colder towards inside. Okay, next we are going to look for the graph. Okay, for graph, this was the equation that we used just now to calculate the temperature. Okay, for the graph, okay, as you can see for the graph here, the graph is of temperature of wall at x, which is the heating time. So this is the axis of temperature and this is the heating time. So as you can see, for the blue line, which is at the surface of the wall, which is x equals to 0, it goes up very fast towards the end, followed by the x is equals to 0.01 meter from the wall surface, which is quite near to the wall. So the temperature gradient is almost same as the wall surface, big difference, but for the x equals to 0.05 meter from the wall surface, which is a bit further inside, the temperature rises very slowly over here, and then gradually increase towards upwards, but it's quite colder towards x equals 0 and 0.1 meter from the wall surface. So here we can conclude that for the distance from the wall surface to the source, it's quite the heating will be more sufficient and more efficiently carried out at the surface rather than inside of the brick. So that's all. Thank you.